Okay, so we're going to continue on talking about some properties of the integers, and we're going to see useful technique and some proofs which you have seen maybe in the analysis course is a principle of mathematical induction, or PMI. Sometimes this is called the weak form of the induction. So we'll get two forms of induction. The setup is P sub n is a statement about the positive integer n. Suppose two things. The first is P sub 0 is true. The second is if P n is true, then Pn plus 1 is true. So these are the hypotheses. You have a statement that meets those conditions. Call this P naught, or we'll call this P sub 1. Positive integers, we start at n equals 1. We'll see, though, actually, you can start this at any integer. So you have these two properties. Then we're able to conclude Pn is true for all positive integer n. So the setup, you have a statement that is true about the integer 1, and it also has a property that if you assume the statement is true about the integer n, you're able to prove it's true about the integer n plus 1. Then, in fact, Pn must be true for all positive integers. That first step is sometimes called the basis of the induction, and the second step, proving that implication, is called the inductive step. And you can actually show this is true for any integer n greater than or equal to k. So you don't have to start at P1. The statement may be false for P1 and P2, but if it's true for some integer k, and then it's also true that anytime Pn is true, Pn plus 1 is true, you're able to then, if you have those two conditions, you can still conclude that Pn is true for all positive integers. So as kind of a basic one, we'll prove a basic summary first. So let's first use PMI first. To prove a well-known formula, the sum of the first n integers is equal to that. And there's a lot of visual ways. This is a rich topic here of visual ways of proving it, or some counting arguments for that to get the idea. But we'll just give an induction. So induction often is a formal way of proving something. It might not do the insight to try to show why this is true. So let me first kind of just prove this. So let's start the basis. We start with n equals 1. Well, 1, if we look at 1 plus 1 times 1 over 2, 1 and equal 1, so P1 is true. So that completes the basis. The inductive step. And again, this is in the notes as well. What we do is we assume 1 plus 2 all the way up to n is given by that formula. And we need to prove that formula. So let's see why this is the case. So we'll start over here. So our sum, if we go from 1 to n plus n plus 1, that would then give us these first n terms by the inductive assumption would equal this plus n plus 1. So if I add up the first n plus 1 integers, it would be that sum, which is n times n plus 1 over 2. And then we can rewrite n plus 1 as 2n plus 1 over 2. So that would then give us n squared plus n over 2 plus 2n plus 2 over 2. But we add these two fractions together, that would be n squared plus 3n plus 2 over 2. And we'll just adjust the camera now for this. This would be n squared plus 1. So let me adjust the camera. And I can zoom back a little bit. And so again, that's where we were at. So what you missed again, I took the sum and I applied the inductive step to use the formula for the first n terms. I just added that last n plus first term in there. I got a common denominator and got that. And then with this, actually we'll factor, right, as n plus 1 times n plus 2. And that's as required over there. For the formula for the inductive step. So this completes the inductive step. And so then by the principle of mathematical induction, we can use this formula for all n greater than 1, greater than or equal to 1. And 0. So that's a straightforward application of the principle of mathematical induction. Okay, so how do we prove the mathematical induction? Why is this true? And we're going to prove it using the well-ordering principle. So again, this is in the notes as is everything. And again, there's also another induction that I gave in the notes. I'll leave that maybe to you just to read through the notes. I'm proving an inequality that actually where P1 is false, you actually, I think P3 is the first time that you're able to prove the first statement that's true. So that's just a point in induction. You do not have to start with P0. You can start with any positive integer, or P1. And actually, some common in induction, you can actually start induction proofs with 0 as your basis case. Okay, so let's move in just a little bit. That looks good. Okay, so we'll go on and see why this is true for the induction. So we're going to prove by contradiction. Okay, so suppose Pn is false for some positive integer n. And again, since we're dealing with integers, really the inequality n greater than, strictly greater than 0 is the same as the inequality n greater than or equal to 1 for integers. Okay. So there exists a k that's a positive integer with pk false. So let's look at, let S be the set of all n such that, well, first n is a positive integer and Pn is false. So that's our set S. So because k exists by assumption, we assume that Pn is not true for every integer. So there's some integer k for which it's false. So k is an element of S. S is not the empty set. By the well-ordering principle, there exists a least or minimum element M and S. Okay, now recall that P1 is true by assumption. Maybe I should have paused to say what is our assumptions of this. The assumption is that P1 is true, and anytime Pn is true, Pn plus 1 is true. The conclusion we want is Pn is true for every integer n. So what we do is we assume it's false. So P1 is true. Well, I think that means m has to be greater than 2, because Pm is false. So m can't be 1, because that's not false. M's got to be greater than or equal to 2. Why is that important? That tells us that m minus 1 is a positive integer. Now M1 is not in S because M is the minimum integer in S. So M1 can't be in S. That means that Pn minus 1 is false, is true. Because S is all these integers for which P of that integer is a false statement. And since M minus 1 is not in there, Pm minus 1 is not false, so it must be true. But by the second condition of the hypothesis of Pm of the principle of mathematical conduction, we can conclude Pm is true. But that's a contradiction. After all, M is an element of S, so Pm must be false. So because of that contradiction, what produced this contradiction? This K right here, the idea that the assumption that there exists an positive integer with Pk false. So, therefore, Pm is true for all n greater than or equal to 1 and an integer. So that's how the principle of mathematical induction can be derived from the well-ordering principle. And I'll leave it to the notes to some examples. Sometimes if you don't, often with inequalities, if the statement of mathematical induction is an inequality, it may not work for P1 may not be true. But perhaps Pk is true for some integer k. Then what you're able to prove by mathematical induction is that Pn has to be true for all n greater than or equal to k. But I'll let you refer to the notes, and you can always email me, or we can go through my office hours using some Echo 360 or some way to communicate in that. But hopefully the notes should be detailed enough, and we'll move on and give a statement of what's called the strong principle of mathematical induction. So usually if I just say the principle of mathematical induction, I mean the regular, what I've just written, as opposed to the strong principle of mathematical induction. Okay, strong form of principle of mathematical induction. So the statement is still, let Pn be a statement about the integer n. Where what? Once again, we have P1 is true. And 2, what makes it strong is that given any positive integer n, if pk is true for all integers k with k between 1 and strictly less than m, then Pm is true. So again, rather than maybe in this time doing it for k less than or equal to m plus 1, m, and showing that p m plus 1 is true, the way I've worded it in the notes is let it be true for all integers less than or equal to m. So let's maybe actually alter this definition slightly. Now let's put an equality here. Then Pn plus 1 is true. So it's really the same idea as what I just erased, right? You have a statement that's true for all integers up to a point. If you have that, then you're able to conclude the next one is true. And so that's probably something we'll also alter in the lecture notes as well, just to make it consistent with this. So let's prove this. And what we do is the proof of this. We use just the regular principle mathematical induction on the statement Qn, where Qn is the statement Pk is true for all integers k between k and m. So we're going to prove Pqn, we're going to prove this statement is true. Notice where the variable k is here, but the statement Qn is here. So let's go to prove this. Let's start with the basis. And Q1 is equivalent to P1, which is true by the first condition right over here, that P1 is true. Right? Something is true for all integers k between 1 and 1. Well, that's just the same as being true exactly for 1. So now the inductive step. So we assume Qm and derive Qm plus 1. Okay, so So Qm plus 1 is the statement. Let's write what that is. Pk is true for all integers k between 1 and m plus 1. So, by condition 2, what do we have? We have that this statement is, so that's Qm, that's what we're trying to prove. So we can use condition 2, assume Pn is true, so we know Pk is true for k between 1 and m. So since we have that, what can we conclude? We can conclude Pn plus 1 is true. And so what will that tell us? That then tells us that, well, Pk is true for all integers up to m. And then we're using condition 2, Pm is true. So this means that Pk is true for all integers between k and kn plus 1. K and all integers k between 1 and n plus 1. But that statement is exactly Qm plus 1. So that completes the inductive step, right? Using the assumption that Qm is true, we're able to prove that Qm plus 1 is true. Since we also proved Q1 is true, by the ordinary principle of mathematical induction, we get Qn is true for all integers n. So I'll be erasing this board and writing that over there. So I'm going to be able to conclude that the statement Q sub m is true for every integer m. So the ordinary principle of mathematical induction Qm is true for all positive integers m. In particular, Pm is true for all integers, all positive integers, m. Just as we were trying to conclude. Actually, I guess I need to see I've left something out on the board, so we'll scroll over here for just a second. I think I left the conclusion off. We've got the statements 1 are true. So this strong form of induction, if you look at it, maybe we can even zoom in a little bit. I've given you the conditions 1 and 2. I haven't given you the conclusion. So Pn is a statement about the integer n where we have these two conditions. Then, in fact, Pn is true for all positive integers n. So that's the conclusion. Just like the regular principle of mathematical induction, but in this step, the implication isn't just Pm implies Pm plus 1, but the implication is that P1 and P2 and P3, etc., up to Pm implies m plus 1. So that's called strong because in the inductive step, instead of assuming one statement, Pm being true, you get to assume m statements are true. Pm is true, Pm minus 1, Pm minus 2, etc. And the classic use of this we'll see in a second involves the fundamental theorem. Well, maybe not quite a second, but we'll see shortly involves the fundamental theorem of arithmetic. And so we'll introduce some notation for that. And some definitions. So, recall last time we talked about division and divisors. And we have two integers, a and b, not both 0. Are said to be relatively prime if, I believe my if can fit in there, if basically their greatest common divisor is 1. And an integer p, integer p strictly greater than 1 is said to be prime if its only divisors, well, everything is divisible by 1 and itself. And a prime number are those numbers where that is the only divisors. And so we'll prove now a theorem of Euclid's lemma, theorem let A, B, and P be integers with P prime. If P divides the product of A and B, then P must divide one of those factors. Just a simple example with this, I'll maybe put it over here. Note, where does the prime come into play? Six divides 12, which is 4 times 3. But 6 divides neither 4 nor 3. That doesn't violate Euclid's lemma because 6 is not a prime number. So let's run through the proof of this. So for the proof, we look at some cases. So we're going to look at two cases. The first case if P divides A, so maybe we should click. So again, we start with assume P divides A times B. If P divides A, that's great. We are done. Right? Because we're allowed, the conclusion is either P divides A or P divides B. If you go back in the board, here you see this N should be an OR. So here you get to change something in your notes. We'll mess up this nice camera work I have and zoom in. And you see the statement there, this should be an OR, not an AND. Okay, so we're done in the case that P divides A, we are finished. If not, what? If not, since P is prime, the greatest common divisor of P and A is 1. Because a prime number, if P doesn't divide A, there's no way that that they could have a common factor. Because the only possible common factor P could have is multiple, would be P. So the greatest common factor is 1. So you might recall the Euclidean algorithm allowed us to express the greatest common divisors as a linear combination. So there exists two integers, we'll call them S and T, with S times P well, S times A, we'll say, and T times P is equal to 1. Also, there is an integer U with AB equals U times P, because P divides the product of AB. So what does this tell us? Then if we look at B, what is B equal to? B is equal to, well, 1 times B, B times 1, B times SA plus TP. But shuffling around, we have, that gives us SAB, which is SUP plus TP, or SU plus T times P. So what does that tell us? I think that tells us P divides B as required. Since we've gotten B is equal to an integer times P. And then, can you follow this inequality? This equality came from SAB, but AB is SUP. So SAB is the same as SUP. And this would just be T, here I should distribute it through the B, this would be TBP. So it's actually S times U plus T times B, all times P. So that proves it. And then we also have a corollary of Euclid's lemma. Suppose we have A1, A2 up to AN integers, and P A prime, where P would divide A1 times A2 all the way up to AN. Then P divides AI for some I. And I'm not going to run through the proof of that. It's in the notes. It's just a nice application of induction. And applying Euclid's lemma. Again, you can read through the notes. Kind of the highlight is you can maybe think of this as a product of A1 to AN minus 1, again, times AN, so if you look at this product, think of it as A1, AN minus 1, up to an. So I'll just sketch the proof just so it's in the notes more completely. So you can think of this whole number as your a and this is your b. If p divides the product, p divides an, well, would meet the conclusion. If not, by Euclid's lemma, p divides this product of n minus 1. But that's tailor-made for the inductive hypothesis, which we can then include p must divide one of a1, a2 up through an minus 1. So this allows us to use one of the prime examples of where the strong form of induction is useful. I should say anything that can be proved by the strong form of induction can also be proved by the regular form of induction. It just may be a lot harder. So let's look at a statement of this. And actually in this algebra course, we'll kind of come down to a generalization of this structure statement. So this is a very deep, important structure statement. So it's the fundamental theorem of arithmetic. And again, I think of this as being basically saying that primes are the building blocks of the integers. So let me first move this camera over, make sure I can capture all of it. And that's good enough. There we go. That seems like it's got a fundamental theorem of arithmetic. So let n be an integer, say it's strictly greater than 1. Then, and this fundamental theorem of arithmetic, like the division algorithm we saw in an earlier lecture, has two pieces, an existence and a uniqueness. First is you can factor it as a prime. So n is either a prime or a product of primes. And second, the factorization is unique up to order of the factors. So if we say factor 6 as 2 primes, 3 and 2, we consider sort of 2 times 3, 3 times 2, those are unique. That's the same factorization. So what this means if n is P1 up to Ps, and n is also Q1 multiplied up to Qs, 2 factorization into prime, where Pi's and Qi's well, let's say Qj are prime, I between 1 and S, and J between 1 and T, Then maybe I'll take advantage of this space over here and get the conclusion is first that the number of factors are the same, and we may have to rearrange, but Pi is equal to Qi. For I between 1 and S, or 1 and T. S and T are the same thing. So that's a statement of the fundamental theorem of arithmetic. Basically, I think of it as saying the primes are the building blocks, unique factorization into primes. I'll express this in another way in a second once we get to the proof. But let me just say in this order, these primes need not be unique. So for instance, 9 could be factors as 3 times 3. Okay, but let me, before I state this proof, just state it another way. And the other way of stating it is, assuming the primes are unique, let's group together the primes, the same primes. The alternate version is, if n is in Z, which is greater than 1, there exists unique integers Si, which are greater than or equal to 1, or let's call these AI. And primes Pi, where I is between 1 and S with some S and Z, S greater than or equal to 1. Then if you take the prime factorization, all the P's that are the same, so let me actually make this distinct. Primes Pi. So n would be P1, A1, P2 raised to the A2, up to PS raised to the AS, where Pi is not equal to Pj for I not equal to J. So the way to make it distinct primes is all the primes of one type you gather and do that. And so continuing on, if A equals P1, A1 up to PS, AS, and B equals P1, B1 up to PS, B sub S, where AI and BI are integers that are greater than or equal to 0. And the PIs are distinct primes. Then the least common multiple of AB is PI EI, or P1 E1 P2 E2 PN EN. And the greatest common divisor is a similar factor in PI let me have it correspond. Well, let's call this PI EI up to PI EN. And just so it's consistent with what I wrote in the notes, let's label these subscripts D1, D2, DS. Where EI is going to be the minimum of each common prime factor. Minimum of AI, BI, the exponents. And DI is the maximum of AI, BI. Again, the reason, first of all, a couple comments you may have about this or a question is what happened. So let's go back to the screen for a second and go over this. And while I'm talking, one thing is, what if these factors are not common? What if there are no common prime factors? But that's what allows us to have the exponents here being greater than or equal to 0. So if some prime factor occurred in A but didn't occur in B, we would just set that B exponent equal to 0, so you have a 1 there. And unlike the Euclidean algorithm I used in the last class, this way is how we usually find the greatest common divisor. So again, sorry for that camera work, we've just got it posted now. Sort of an alternate statement of that fundamental theorem of arithmetic is we take the prime factorization, let's group all the primes together. We can write it uniquely as a product of primes where each exponent, each prime actually appears. So then it's A times B. If they may have very different prime factors, but that's okay because if you allow the exponents to be greater than or equal to 0, that puts a 1 in there, so then they really do have all the same factors. Right? You could say 5 has 3 as a prime factor, 3 to the 0. So that's, if you look at it that way, then to get the least common multiple, you would take all these primes and you look at the biggest of each of these two factors. And if you take the greatest common divisor, you look at the smallest. Okay, so we'll get to the proof of the fundamental theorem in arithmetic in just a second. I'd like to maybe just work in a simple example or two. Okay, and I think I should also maybe formally define the least common multiple. We've defined the greatest common divisor. Actually, the tact I took was to define it as a minimum element of the set, of a certain set, and then show it has the properties that we usually associate with the least common divisor, with the greatest common divisor. Let me define the least common multiple of A and B. So the least common multiple of A and B is the positive integer, let's just call it K. Where first of all it's got to be a common multiple of A's, of A and B. So K is a multiple of A, that means A divides K. So there exists X and Y and Z, where K is some multiple of A, and K is also a multiple of B. And what is least common multiple? So what if there's another common multiple? If M is in Z with let's make it positive. Say there exists, it's a multiple of A and B, so there exists W and V with N equals W times A and M equals W times V times B. Then what makes K the least means that M itself must be a multiple of the least common multiple. So there exists a Z in Z where this common multiple M is just a multiple of the least common multiple. So that's a definition of the least common multiple. So as an example, let's find the GCD of 24 and 18 and the LCM of 24 and 18. So 24 is 3 times 8, which is 3 times 2 cubed, breaking it down to 5 factor. And 18 is maybe 6 times 3, which is 3 times 2 times 3, so that would be 3 squared times 2. So what's the greatest common divisor? This is to the first power. Minimum of 1 and 2 is 1, so it would be 3 to the 1. Minimum of 3 and 1 is also 1, so times 2 to the 1, or just 6 would be the greatest common divisor. The least common multiple would be 3 to the 2 times 2 to the 3, which is 9 times 8, which is 72. Now we should work another example where there's here all the primes they have in common. Maybe I should work an example where there is not a common prime. So in example 2, let's find the GCD of 42 and 50, and also the LCM of 42 and 50. So 42 is 6 times 7, which is 2 times 3 times 7. Fifty is 25 times 2, which is 2 to the first times 5 squared. So what's the greatest common divisor? The minimum of 1 and 1. And here, but we can really put a times 5 to the 0 here, and times 3 to the 0 times 7 to the 0. Because those are all, anything raised to the 0 apart from 0 is 1. So the minimum of 1 and 1 is 1, so we have 2 to the 1. The minimum of 1 and 0 is 0, so we have 3 to the 0. I won't bother to write that. I guess why not? The minimum of 0 and 2 is 0, so it would be 5 to the 0. The minimum of 1 and 7 is 0. And that does it. 1, 1, 1 times 2. The greatest common divisor is 2. What about the least common multiple? The maximum of 1 and 1 is still 1. The maximum of 1 and 0 is 1. The maximum of 0 and 2 is 2. And the maximum of 1 and 7 is 7. So it would be 6 times 25 times 7. Boy, this is pretty hard to do mentally, right? 42. I can run to the calculator. 42 times 25. And if I do that monthly, what I'll do is I'll do 42 times 100 is 4,200. Then if I divide that by 4, divided by 2, it's 2,100. And divide that by 2, it should be 1,500. And I'll pull up the calculator on the computer in the background just to confirm that. I'll go to the calculator. And so I have to multiply 3 times 5 times 7 times 2. I think I'm off by an extra 0. Oh wait, let me clear that again, hold on. Let's see, that should be 2 times 3 times 25 times 7. And it is indeed 1050. Okay, so that concludes some talk about the integer. Once we'll run through the proof of the fundamental theorem, which again is done in the notes, but I'll run through some of the ideas. It's an application of the strong form of induction. And so we have to prove two things. We have to prove any integer n greater than 1 can be factored into prime. And then we have to prove the uniqueness, but we're going to prove separately, separate proofs for each, separate induction proofs. So we start proof that, so this statement here is a Pn initially. So we'll first use induction to prove that. We're going to use the strong form of induction. So the basis case, as we've talked about, we can start the basis at n equals 1 is not really true. 1 is not a prime, so it cannot be factored into primes. So the basis n equals 2, 2 is a prime. So P2 is true. Now the inductive step. And we're going to use the strong form of induction. So we assume P1, P2, up to P n is true, and try to show Pn plus 1 is true. So we need to show, that is, what is Pn? Pn is just that n plus 1 is a product of prime. Okay, so or a prime. If n plus 1 is a prime, we are done. What if it's not a prime? If not, then there has to be integers a and b that are both strictly less than n and strictly greater than 1. Strictly less than n plus 1, strictly greater than 1. With n plus 1 is a product, right? A prime means there's no other divisors except for 1 and n plus 1. That's what it means for n plus 1 to be prime. So if we assume n plus 1 is not prime, it's got to have two factors. It's got to have a factor that's between 0 and strictly greater than 1, strictly less than the number itself. But both a and b are less than or equal to n. So each is either prime or a product of primes. But then n plus 1, which is a times b, is also a product of primes. So again, you see where the strong form of induction comes into play here, right? If this was just weak induction, all we would be able to conclude is that n is a product of primes, or a prime, nothing else. But with the strong form of induction, since a and b are both less than or equal to n, we can conclude that the statement is true about those integers. Right? Somewhere among this list, a and b are one of these indices, somewhere between 1 and n. And so by the strong form of induction, we're allowed to assume that's true. So what have we done? We proved the basic case, and we showed that anytime P1 up to Pn is true, Pn plus 1 must be true. So what is strong form of induction allows us to conclude that Pn is true for all n. So let me prove that over here. So Pn plus 1 is true. By the strong form of induction, Pn is true for all integers in z greater than or equal to 2. So we've got the factorization in the prime. Now for uniqueness. I guess I could, maybe Pn is already used, so let Qn be the statement n is factored uniquely into primes. So what's the basis case? N equals 2. All other primes are greater or equal to 3. So clearly they cannot be factors of 2. Right? Certainly, 2 is the only prime that 2 is equal, and we can't write 2 as a factor of primes because all the prime numbers are greater than 2, and so none of them can be factors of 2. Now the inductive step. And again, we use strong induction. Assume for any integer k with k less than or equal to n, the factorization into primes is unique. So that's where we are. I'll just scoot over here, erase the board. Okay, so we need to show this is true for n plus 1. So we already know the existing part, so suppose n plus 1 equals q1 up to qt, and it's also p1 up to ps, where pi and qj are primes. Well, what do we have? Since certainly P1 divides n, right? There it is the factor, or it divides n plus 1. We have by that corollary of Euclid's lemma, Pi divides Qj for some j. And just by reordering the Q's, we can assume P1 divides Q1. Right? If P1 divides Q8, well, let's just call 8 1. Let's just change the order, right? Q1 is the one that goes first. The order of multiplication is commutative. It doesn't matter which way we order the factors. So what do we have? Q1 is prime. And P1 being prime is greater than 1. So Q1 would have to equal P1. Right? Because the only things that can divide Q1 is Q1 and the number 1. Well, P1 divides Q1, but P1 is not the number 1, so it has to be Q1. Then we let K be n plus 1 over Q1, which is the same as n plus 1 over P1. Then, since we took n and divided by n plus 1, divided by a number greater than 1, k is less than, strictly less than n plus 1. And since we're dealing with integers, that means k has to be less than or equal to n. And again, this is where the strong form of the induction hypothesis is going to come in. If it was just weak induction, the only thing we can conclude would be that the only thing we would be allowed to assume for the inductive step is that n is factored into primes uniquely. But with the strong form of induction, we're able to assume any integer less than or equal to n is factored into primes completely. So we also have that k is then going to be, on the one hand, P2 up to PS, but it's also got to be Q2 up to QT. Right, remember, k is just n plus 1 divided by q1, but n plus 1 is q1 all the way up to qt, so if we divide by q1, we just are left with q2 up to qt. N is also p1 up to ps, and if we divide by p1, that cancels, and we're left with p2 up to ps. But by the inductive hypothesis, since k is less than or equal to n, we have, how many factors are here? 1 up to s, so s minus 1 factors. Here we have t minus 1, so t minus 1 factors. And after reordering, pi is equal to qi for I equal 2, 3, all the way up to t. And that was, And then also this also means, since there's s minus 1 factors, has to equal t minus 1 factors, so s minus 1 equals t minus 1. That also means s equals t. So we've got it, right? By the corollary to Euclid's lemma, we saw that P1 is equal to Q1, and then the inductive hypothesis takes care of that. We can conclude that S equals T, and then that P2 is equal to Q2, P3 is equal to Q3, all the way up to PT is equal to QT. So this concludes our lectures on the integers.